Ladies and gentlemen, Dr. Lawrence Krauss.
Okay, well, thank you for this that impromptu introduction and this impromptu talk, apparently. So I got asked to speak about the universe of nothing, and we have very little time, apparently. So since, in fact, the first time I gave a talk on that with that title was at the American Atheists meeting. I don't want to repeat that as much as I'd love to. I will, but I'd like to summarize some of it, and I'd like to focus on some things I didn't talk about in that video that seems to have been seen so often. So I'm going to give you a brief overview of cosmology, but not enough that you'll actually understand anything I'm going to say. And then I want to talk about the implications for nothing that I didn't talk about so much in the lecture that many of you have heard, because I figured you wouldn't want to, well, maybe you want to see the same thing over again, I don't know. But so that was, by the way, I think I probably may even have used that quote before. But I love this quote from Louise Bogan, because it really, to me, emphasizes what science is all about, which is really getting to the beginning. And I run an institute in Arizona called the Origins Project, and it's really, and if you think about it, at the forefront of every field of science, origins are the key things. And it's true, of course, for the universe. And what's truly amazing is that science has progressed to the point where the questions, why something rather than nothing, which many people have thought is a religious or philosophical question, has become a scientific one, in spite of some moronic philosophers who've just written for the New York Times today. Anyway, so what I want to do is, well, let's just go. So the question that I really want to address is this question that I kept getting hit at a lot after the last lecture and in the last many years as a cosmologist by religious people, which is, why is there something rather than nothing? That seems to be the final step where they say, aha, you can get rid of God from the origins of life, you can get rid of God from everywhere else, but you can't get rid of God from the creation of the universe, because you can't create something from nothing. Out of nothing comes nothing, as philosophers said thousands of years ago and maintained ever since. And of course, philosophy is a field that hasn't progressed in 2,000 years, where science has. And so what I want to do is, instead of being guided by what we like to be or what we think is logical, I want to be governed by the universe. Now, this is a simple way of answering the question, why is there something rather than nothing? Saying in the beginning and then writing a whole book about it. And, but that doesn't do anything. That doesn't answer any questions. It just asserts something. It doesn't explain anything. And so that's not the way we should do things. We don't understand the universe by thinking about it. We understand the universe by probing it. And so I want to go back to this picture, which is the universe, the actual universe we live in, the real universe. And as I often say, I now live in Arizona where you can see these, but I used to live in Cleveland, and I used to have to tell audiences that these were stars, because they'd never seen them. But the remarkable thing about this beautiful universe in which we live, full of stars and wondrous things that we see through our telescopes, is that our picture of it has changed more in the last 100 years than it has in the last several thousand. It's completely revolutionized, and really that's what I wanted to celebrate when I wrote the book, and that's what in general I want to celebrate, because we are like the early map makers. We are just beginning to map the universe on larger scales. A century ago, the universe consisted of a single galaxy located in an eternal empty space that was static and eternal. And of course, everything has changed. We now understand there are 400 billion galaxies in the observable universe. The universe had a beginning 13.7 billion years ago, except in the state I used to live in, except in Ohio and Arkansas and a few other places. But, and that's changed everything. And so anyway, let's talk about it. So I want to just give you about 5 or 10 minutes on cosmology, and then another 10 minutes on implications, and then maybe have some time for questions. I don't exactly know how it works. But so I draw this picture, which is really unfortunately confusing and misrepresentative, because Einstein demonstrated that space curves in the presence of matter and energy. And that means our universe, space itself is dynamical. Now, I can't draw for you curved three-dimensional universes, but I can draw curved two-dimensional universes. And so you shouldn't take these pictures literally, except to say that a curved three-dimensional space can exist in one of three different geometries, so-called open, closed, or flat. And in the two-dimensional space, we can draw those pictures. It's a closed universe, an open universe, and a flat universe. The surface of a sphere is a closed universe, and the surface of a saddle is an open one, and an infinite piece of paper, a flat piece of paper, is a flat universe. But the key point, and what's important about all of this, even if we can't picture it in three-dimensional space, although I can picture some things in my mind in a closed three-dimensional universe, if I look far enough in that direction, I would see the back of my head, because space would curve, even if you can't picture it, all three-dimensional universe would curve. But when I talk about a flat universe, I don't mean one that's flat like a pancake. I mean one that's the universe you always thought you lived in, where the three perpendicular axes remain perpendicular and light travels in straight lines. In a curved universe, light curves. And in fact, I'll talk about that in a moment. So in any case, the key thing is that we used to think that in a closed universe, our universe would expand, stop, and contract in a big crunch, the reverse of a Big Bang. An open universe would go on expanding forever, and a flat universe would be the boundary between the two of them. And that's why I got into cosmology as a particle physicist, because I wanted to be the first person to know how the universe would end. It seemed like a good idea at the time. And by determining which universe we lived in, I thought I could do that. And how can we determine which universe we live in? Well, the geometry of space is affected by the amount of matter. So to determine the geometry of space, we simply have to weigh the universe. It's a homework assignment. But we can, and it's a story that's a remarkable story, and I've tried to tell in the book of how we've been able to weigh the universe, but I want to show you the results. You simply stand on the shoulders of giants if you want to weigh the universe, and in this case using gravity. And if you want to weigh the universe, use gravity, because anything that weighs something affects gravity. And so what I want to show you is a picture that's allowed us to weigh the universe. This is a picture, a Hubble Space Telescope picture, one of many beautiful Hubble Space Telescope pictures. One of the great things about this picture is that every dot in it is not a star but a galaxy. So just think about that. Every one of those dots is a galaxy. Each galaxy contains 100 billion stars or so. This is a cluster of galaxies. Clusters are the biggest bound objects in the universe. That means anything that could fall into anything will fall into a cluster. The size of this is about 10 million light years across. So it takes light 10 million years to cross from one end of that to the other. Most galaxies live in clusters. Our own galaxy lives in a cluster, the Virgo cluster of galaxies. But this cluster is 5 billion light years away. 5 billion. That means the light left from it before the Earth and Sun formed. The light that was taken by recorded in the camera that took that picture left that cluster before our Sun even formed. And it means that most of the stars in this picture no longer exist. And the civilizations that may have lived around those stars no longer exist. Every time you look at a picture like this, your mind should be expanded and your imagination driven in a way that, as I say, the universe can drive our imaginations in a way that our simple human stories can't. The universe continues to surprise us in ways we never would have imagined. And every day I'm surprised if I'm not surprised. Because every time we open up a new window on the universe, we're surprised. In any case, when you look at this picture, it's a remarkable picture because you see these blue things, which don't look like the rest of the galaxies. And those blue things are an example of the fact that space is curved. Because Einstein realized if you have a big mass, object here, light will bend around that mass. So if I have a light source behind a big mass, the light rays will come around, bend, and converge again, and cause it to be a lens, like the lens in my glasses. It can magnify images. Or if I had a cut glass goblet and I looked at this room, I'd see many images of you. And what we now realize is that those blue images are multiple images of a single galaxy located another 5 billion light years behind that cluster, 10 billion light years away from us. It's a remarkable phenomenon. It shows us that space is curved. It's beautiful. In fact, Einstein predicted in 1936, and if I had more time, I would have given you a wonderful story with some images about Einstein's predictions, but I don't have time. It is in the book. But I wanted to show you, but the neat thing is that we now understand how gravity works. So we can ask, how much mass is there in all these galaxies in order to produce this image? How much can these galaxies bend space? It's a complicated mathematical inversion, but when we can do it, we get this picture. This is a picture of where all the mass is in that image in order to create the image, and the spikes are where the galaxies are. But what you notice is there's a huge mountain of mass. Most of the mass in that system is where the galaxies aren't. 40 times as much mass exists in that system, as you can see. And that's one of the first indications, although it wasn't the first indication in the history of science, but it's one of the most profound and direct indications that most of the mass in the universe is invisible. 90% of the mass in the universe doesn't shine. And in fact, it's not even where the galaxies are. In this case, it's around the galaxies, but it's not in the middle of them. And there's so much of that stuff, and physicists call it dark matter because we're not very creative. But most of that stuff, there's so much of it, we know it isn't made of the same stuff as you and me. It's made of some new type of elementary particle that we have yet to discover. And I can't go into the reasons, and I'll be happy to try and answer some of the questions. Why are we almost certain it's not made of protons and neutrons, it's made of something else that's going right through your bodies here as you nod off during this lecture. Okay? And that's profoundly interesting because, first of all, it tells us that most of the universe is other stuff. We are a bit of cosmic pollution in a universe full of dark matter. But just wait. So when people talk about a universe created for us, we are just a sideshow. But if you began to feel insignificant, just wait. In any case, what we've discovered is when you add up all the matter in all of these clusters of galaxies, we come up with this beautiful thing called omega. Physicists, when they have an important number, they give it a Greek letter to make it sound important, to make it sound scholarly. And omega tells us what the ratio is of the actual amount of stuff in the universe divided by the amount of stuff you needed to make an exactly flat universe. A flat universe is a boundary between an open universe and a closed universe. So if omega was 1, we live in a flat universe. If omega is less than 1, we live in an open universe. If it's bigger than 1, we live in a closed universe. And lo and behold, after 80 years of trying, we finally have been able to measure that there's only 30% of the amount of stuff needed to make the universe flat. So we appear to live in an open universe. We've answered the holy grail of cosmology. But there's a problem. And that theorists like me knew the answer. We always know the answer. We're not right very often, but we always know the answer. And the answer is that we live in a flat universe. We knew we live in a flat universe because a flat universe is the only mathematically beautiful universe. For reasons I'll show you in a second. And these damn observers, and in this crowd I can say damn thankfully, these damn observers kept coming up with the wrong answer. It was very disconcerting. But this is a very indirect way of measuring the geometry of the universe, because you try and weigh the universe and you plug the answer into Einstein's equations and you work through a bunch of stuff and you try and figure out the geometry of the universe. But it would be better to measure the geometry of the universe directly. And how can you do that? And I want to go back to that picture I showed you. The way you can do it is by measuring a triangle. Because you notice that, in fact, on a flat plane, a triangle is a triangle. But on a sphere, you notice that a triangle is such that the sum of the angles is no longer 180 degrees. Because these straight lines curve on the surface of a sphere. And as I've often said, on the surface of the Earth, I can draw a triangle by going along the equator, making a 90-degree angle to the North Pole, making a 90-degree angle, and going back to the equator, 270 degrees. If I drew a big enough triangle on the surface of the Earth, even in Missouri, I could show that the Earth isn't flat. Okay? And you notice that the sum of the angles is bigger than 180 degrees for a closed universe and less for an open universe. Well, even though these pictures are two-dimensional guides to your eye, the same thing is true in 3 dimensions. So if we can measure a big enough triangle, we can measure the curvature of our universe, and we've been able to do that in the last 10 years. We've been able to do that by looking at a signal from the Big Bang. The cosmic microwave background radiation, the afterglow of the Big Bang. Again, because I don't have time to give you an adequate explanation in this particular lecture, but I've done in the book and in the other lectures that you've seen. If we look, we know that radiation is coming at us from a distance of almost 13.7 billion light years away. And in fact, when we look at that radiation, if we image it, we can look for lumps and cold spots and hot spots in that radiation. And it turns out the biggest lumps that could have collapsed is that radiation was, the surface that we see was created when the universe was 100,000 years old. Nothing can travel faster than light. So the biggest lumps that could start to collapse, that would know they were lumps, are the biggest lumps that gravity could have traveled across in 100,000 years. And since gravity travels at the speed of light, they're 100,000 light years across. And so we have a ruler on that surface a known distance away from us that's 100,000 light years across. And we can ask, how big does that ruler look on our eyes? Because if the light rays come to us in straight lines, the ruler will look like 1 degree across on our eye. But if the light rays curve, then the ruler will either look smaller or bigger. So we take a picture of that microwave surface, and this is a picture that was taken by a wonderful experiment called the boomerang experiment in Antarctica, with a balloon that took a microwave radiometer around the world, which is easy to do in Antarctica. In the South Pole, you do this. And it took this image of the microwave sky, and the question is, how big are these lumps? How big do they look on our eyes? And this is a different false color image of the same region, and we can create universes on a computer and say, let's lay down some lumps that are 100,000 years across in a closed universe, an open universe, or a flat universe, and compare their size to these size. And you see in a closed universe, these lumps are bigger than these lumps. In an open universe, the lumps are smaller than these lumps, but just like Goldilocks. In a flat universe, it's just right. So we know the universe is flat now to an accuracy of 1%. We can pat ourselves on the back because we knew the answer. No, you shouldn't applaud, because we knew the answer for totally the wrong reasons. Because after all, I just showed you, we weighed the universe, and there's only 30% of the amount of stuff necessary to make the universe flat. So where is the other 70% of the energy of the universe? It's missing. Well, the point is, if that energy isn't where galaxies are, and clusters of galaxies are, it must be where clusters of galaxies aren't. What is where clusters of galaxies aren't? Nothing. And this is the first indication that nothing is not what we used to think it was. I've tried to explain that in small words to philosophers, but as I say, they don't understand. But we now understand, using the laws of quantum mechanics, that empty space isn't really empty. Empty space is this is a picture of empty space, the empty space inside of a proton. And we now know that due to quantum mechanics and relativity, empty space is a boiling, bubbling brew of virtual particles, popping in and out of existence at a timescale so short you can't see them. Now that does sound like philosophy. But it turns out while you can't see them directly, they have an indirect effect. These particles that are popping inside, outside, in and out of space, inside of a proton, are responsible for most of the mass of your body. We can actually calculate how much of the mass of your body these things correspond to, and it's about 90% of the mass of your body. So these vacuum fluctuations, as they're called, are responsible for our own existence. Empty space can have energy. Now, when we try and calculate how much empty space outside of a proton, how much energy there should be in the rest of the universe, we come up with an answer which is ridiculous. It's the worst prediction in all of physics. It's 120 orders of magnitude too large. We didn't understand it then when we first calculated. We don't understand it now. But we do know if we put energy in empty space, the weird thing is that energy, well, all of you know that gravity sucks. Okay? If you put energy in empty space, gravity blows. It's repulsive. It's like anti-gravity. And so if you filled up the universe with the energy of empty space, let's go back here, if we fill it up with the energy of empty space, what will it cause the expansion of the universe to do with time? Well, any universe that's sensible should slow down over time. But if you fill the universe up with an energy of empty space, it'll speed up over time. And in 1998, two groups of astronomers who didn't know what the hell they were doing went out to measure the rate at which the universe was slowing down to confirm that it was full of dark matter, and discovered something which was on the cover of Science magazine. This is the data looking at the expansion rate of the universe as a function of time, basically. And if I draw a straight line through that data set and bring the whole thing down, here. If the universe was slowing down as any sensible universe should do, all of these points here, which represent exploding stars very far away from us, should have fallen along this curve. But they don't. They fall above the straight line. And what does that mean? Well, that means either the data is wrong, which is usually the case, in astrophysics in particular, or the expansion of the universe is speeding up. And if just for fun you ask how much energy should you add to empty space to fit the data, you get just what we're missing. If you put 70% of the energy of the universe in empty space, everything fits. So we now have this picture of the universe where everything fits, but we don't understand anything. Which is the best possible situation to be in science. Because in religion, you understand everything and know nothing. 2 years from now, I'll be seeing that on mugs and t-shirts now too. Anyway, but in science, you know, it's okay not to understand stuff. And the universe is mysterious and wonderful. But we now know that 99% of the universe is different than us. So if you thought, again, as I said, if you thought you were insignificant a moment ago, just wait for 10 minutes. You are completely insignificant. You are irrelevant, and everything we see in the universe is irrelevant. You can get rid of us and the stars, the galaxies, and everything, and the universe would essentially be the same. It's full of dark matter, but more than the dark matter is dark energy. Nothing is the dominant stuff in the universe. So I want to spend the last 5 or 10 minutes now discussing the implications of that. This was the result. I want to make much ado about nothing. I just want to summarize what I said. The dominant energy in the universe resides in empty space. We have no idea what is there. Its existence is probably tied to the beginning of time, and it will determine our future, and our future is miserable. In case you're wondering. Okay. Now this is the reason, and I never got to say it in the last talk, why we knew the universe was flat. I want to take you back to one of your favorite times, high school physics class. If I throw up a coin, it comes back down. If I throw it up faster, it takes longer to come back down. If I throw it up really fast, it doesn't come down at all. There's no ceiling. We teach our students how to calculate that, and here I want to show you, it's going to bring back such good memories. Okay. We teach our students how to calculate that. It doesn't matter. This is the formula. The total energy of this coin has two pieces. A positive piece, we call that the kinetic energy, and a negative piece, we call the potential energy. And it turns out it just becomes bookkeeping. If the positive piece beats the negative piece, the coin will escape. If the sum total of these is bigger than 0, the coin will escape. If the sum total is less than 0, the coin will return. Well, it turns out we can do that with the universe. We look out at galaxies, and here's our galaxy, they're all moving away from us on average as the universe is expanding. And if the universe is the same everywhere, what happens to any galaxy will happen to all galaxies. So we treat this galaxy as if it's a coin, this distant galaxy, and we ask, what is its total energy? If it's positive, it will escape out to infinity, and the universe will expand forever. If it's negative, it will come back, and the universe will collapse. And there are two pieces to the positive, well, to the energy. The positive piece, which depends on the velocity of this, but that just depends on the expansion rate of the universe that we measure. We call it Hubble's constant. The negative piece comes from all of the mass that's attracting this back. And we just add up the two pieces. And if the negative piece beats the positive piece, the universe will collapse. If the positive piece beats the negative piece, the universe will expand forever. But it turns out that this ratio is nothing other than omega, the quantity that determines whether the universe is open, closed, or flat. So if we live in a flat universe and omega is 1, that's the universe we like. What does that mean? That means B equals A. But what does it mean if B equals A? It means the negative piece equals the positive piece. And what does that mean? That means the total energy of every object in the universe, the gravitational energy of every object in the universe is zero. But if you were going to create a universe for nothing, what would you make the total gravitational energy of everything? Zero. That's why we physicists like the flat universe, because only in a flat universe is the total gravitational energy of every object precisely zero. It didn't have to work out that way. But this is the first inkling that something and nothing are not too different. One of the big arguments that ignorant people say about why you can't create something from nothing is, well, they try and invoke physics and say the conservation of energy says you can't start out with nothing and end up with lots of stuff. But once you add gravity, it's completely possible. So let me go take you now briefly through the different kinds of nothing. The first kind of nothing is empty space. The kind of nothing in the Bible. Eternal darkness. A void. Emptiness. Well, the point is we know that kind of empty space can create something all the time. Because remember, I told you, empty space is full of these things popping in and out of existence at a time scale so short you can't see them. But once you add gravity into the mix, and gravity can allow negative energy as well as positive energy, you can create stuff whose total energy is zero. And once you start creating stuff whose total energy is zero, you can create as much as you want. And so the laws of quantum mechanics tell us that nothing is unstable. If you wait for long enough in a universe devoid of anything, you will end up with a universe full of something. You don't need God or anything else. It's not magic. It's automatic. You are guaranteed to have a universe full of something if you start out with nothing. Now, that should be enough. Because after all, I showed you that the nothing of ancient philosophers and theologians will create something. But of course, the minute I say that something can come from nothing, the philosophers and theologians say, well, that can't be nothing. Because we said nothing can't create something, and you just showed us you could, so it has to be something else. As I said, read the New York Times today, and you'll see about that. But it turns out it's even better than that. Because when you apply quantum mechanics to gravity, gravity is a theory of space and time, and space itself becomes a quantum object. And not only can you create particles within space, but in fact, you can create space itself. And in fact, once you have quantum mechanics and gravity, you can create whole universes that weren't there before. So the second kind of nothing tells us that the minute you make gravity a quantum mechanical object, you can have no space and suddenly create space. But what's the only kind of space that you can create that can last forever? Or last long enough that we can ask the question, why is there something rather than nothing in it? It's a universe with zero total energy. Now you may think, hey, he just showed us that only a flat universe has zero total energy and everything works. It's more subtle. I wish I could say that, but I can't. It's just a little more subtle. It turns out we can't calculate the total energy of a flat universe. The gravitational energy in a flat universe is zero, but there's all sorts of other kinds of energy. Rest mass and all sorts of other stuff. It turns out the only universe whose total energy we can calculate is a closed universe. And it has zero total energy. But you may say, hold on, we don't live in a closed universe. Well, it turns out we can ask ourselves, what's the only kind of closed universe that could live long enough for us to live in, to evolve in? And it turns out it's a closed universe that looks like a flat universe. Because most closed universes that you create will collapse on a time scale a fraction of a microsecond long. The only kind of closed universe that you can create that will survive long enough for people to evolve in it is one that blows up at very early times, has lots of energy and empty space. The laws of particle physics that we now understand tell us that we believe that's precisely what happened in the early history of our universe. But when you blow up a closed universe, it's like blowing up a balloon. If you blow it up very large, then it looks flat. And the only closed universe that can survive 10, 13 billion years is one that had this period of rapid expansion in early times, which we predict in particle physics. And then it must look exactly flat. So this next slide basically just says that. that the only closed universe that can survive long enough for us to measure it is one that looks flat. And therefore, the only universe that could come from nothing, in which intelligent life could evolve, is one that looks identical to the universe we live in. So now we've shown that empty space can create something. We've shown if you don't have any space, you can create space. So that should be enough. But people then say, well, it's okay, you don't have particles, you don't have space, but you have the laws of physics. But it turns out we now think that the laws of physics themselves may be accidental. They may arise when the universe arises. And I don't have much time, and I want to end in about 4 or 5 minutes. For reasons, in fact, the discovery of the energy of empty space has led us to the realization that perhaps our universe is unique. If we try and understand why our space has energy, one of the arguments is quite simply that if it had much more energy than we measure, then galaxies wouldn't form. And if galaxies wouldn't form, then stars wouldn't form, and if stars wouldn't form, planets wouldn't form, and if planets wouldn't form, astronomers wouldn't form. So the reason the universe is the way it is because astronomers are here to measure it. It sounds ridiculous, but it might be true. It sounds religious, by the way, too. It sounds like the universe was created for us, but it's not. It's like cosmic natural selection. If there are many universes, we would only expect to find ourselves living in those universes in which we could live. In fact, it would be extremely surprising to find the opposite. Just like bees can see the colors of flowers, not because they were designed to do it, but if they couldn't find the nectar that could allow them to survive. So it's just cosmic natural selection. But if that's true, it means this fundamental quantity, the energy of empty space, is an accident. And if that's an accident, maybe all the concepts of physics are accidents. Everything we know may be an accident. We don't know if it's true or not. But if that's true, we don't need a theory of everything, we need a theory of anything. It turns out, for reasons I won't go into, we have such a theory. It's called string theory. It doesn't predict anything. But if this is true, it means that as our universe formed, the laws of physics formed along with it. And therefore, the last bastion, the last nail in the coffin of those who would say you can't create a universe from nothing is gone. No space, no particles, no space, no laws, no God. Okay. If this is the case, and our universe popped into existence 13.7 billion years ago, it may be a multiverse of universes. In that multiverse, some universes are being created right now. Then the multiverse takes the role of the prime mover of Aristotle, or the first cause of the Catholic Church. It could be eternal. Now when I point that out, and I've argued with Christian apologists about this, they say, you guys just invented the multiverse because you don't like God. But the point I want to point out is we've been driven to this not because of our philosophical predilections, not because we liked or didn't like something. It's because the laws of nature have told us it's probably what happens. And that's the key point. We've been driven to this by looking at the universe. And the universe has told us that it's quite plausible that it came from nothing. And to me, that's one of the most remarkable developments in the history of science, that physics has taken us to the point of addressing this question we weren't supposed to ask. Where does everything come from? And the fact that it's even plausible that the universe came from nothing is something that's worth celebrating. But in deference, I want to end in deference to my friend Christopher Hitchens, who I used to tell about this, and he was writing the foreword for my new book before he died, but he didn't finish it. And in fact, when I told Christopher about the future of the universe, he pointed out that nothing is heading straight towards us as fast as it can be. Because if the universe is expanding faster and faster and faster, then eventually every galaxy we see outside our own will disappear. It'll be moving away from us faster than the speed of light, and in the far future, the universe will become cold and dark and empty. And look just like the universe we thought we lived in 100 years ago, with one galaxy surrounded by an eternal empty void. And when our own galaxy goes, when the stars burn out, there'll be nothing left. So as he pointed out, if the universe is expanding faster and faster and faster, nothing is heading towards us as fast as it can be. And the final answer to the question, why is there something rather than nothing, is really quite simple. Just wait, there won't be for long. And that points to me, and maybe it's nice that my friend Richard Dawkins is going to talk next, because there's a connection between this and evolutionary biology. Because we have this incredible conceit as human beings that we are the pinnacle of evolution, when we really are a stage of evolution. But at the same time, we have this conceit that the universe was created for us and it'll always be this way. The universe we live in now is a snapshot, and in the far future, the universe will be quite different. We are living in a rare time in which we can live. And what that tells us is, in fact, that we should enjoy our brief moment in the sun. It tells us that the universe wasn't created for us, we're a sideshow, we're an accident, but we should enjoy the ride. So to conclude, science has demonstrated that the universe for nothing is not only plausible but likely. More importantly, what we mean by something and nothing has completely changed from the time that classical philosophers and theologians first raised this issue. This is an idea that I can't seem to explain to philosophers and theologians. It's changed. Those questions you once asked are irrelevant now. Science has changed the playing field for those questions, just like it's changed the playing field for the question, why are there 5 planets? As Plato used to ask, or Aristotle, not Plato, but Kepler. Well, there aren't 5 planets, there are 9 planets, and there all are 9 planets because Pluto will always be a planet, don't believe it. Because my daughter did a 4th grade project on Pluto, and she's not going back to 4th grade no matter what. So, but the point is that question is just, it doesn't mean anything, it's not important, it's an accident. What we care about is how are there 9 planets. We want to know the different kinds of solar systems that exist and how many different kinds of planets can exist in solar systems. So the key questions are no longer why is there something rather than nothing. The key questions are how did the universe evolve and how can we find out? That's the important question, and that's the question we're trying to answer, because that involves learning, and that's what science is all about. And the fact that we don't know the answer yet, but we can find what's plausible, is to me a remarkable intellectual journey that's worth celebrating. Thank you very much.
Dr. Lawrence Krauss, everybody.